Hey, John here. Let's take a quick look at the C++ build process. All right. Turns out this is exactly the same as the C build process. Both of these languages work very much the same way when it comes to how you compile and link and assemble your programs. So let's look at the bird's eye view of this diagram over here. What do? You write a program like prog1.cpp. And then you run the compiler, right? G++, and whatever your favorite arguments are, and you give it a name that you say, hey, I want you to compile this program here, prog1.cpp, and then when you're done, I want you to save it in a file called prog1. So I make the executable file named prog1. The stuff over here is that's going to be personal preference. I always put W all in there. What that does is it says, look, if the compiler, the GNU compiler can actually check a whole lot of things. By default, it does not. By putting wall in there, what it does is it checks everything. I've asked it, anything it can check for me, please check, okay? And it will end up generating warnings and things for various situations that are commonly known flaws, mistakes, and it'll even offer suggestions and things like that. All right, so that's all been coded in over the years. A lot of people get frustrated. Why doesn't it tell me this? Well, because it's not technically supposed to, and they added this flag specifically for those things. Now, those are just warnings, okay? Adding this flag over here says, treat all the warnings as the same as a formal error and halt immediately. All right? And I do this because in a large project, when you're compiling, the output of, large make files and builds and stuff just spew text all over the place. And it can go pretty quick if you write, small files. So by telling it to stop on the hint of any kind of a warning, it will halt my build process, and I can easily see error messages and things like that, or in this case, sometimes they're just warning messages, and then go back and fix them. All right, don't blindly forge ahead and still create an executable program that probably won't work. Okay, that's what this thing does. Then after that, you can, if you want, select a specific version of C++ in this case, right? I want to say, in this case, I want to use the C++ 11 specified language features. All right, and there's an 11 and a 14 and a 17. There's going to be a 20. This is just which generation of the language you want to use, right? And I already mentioned -O says store my executable program here, and again you have the source code. Okay, so let's look and see what really happens here. You don't just run the compiler and it just spits out your program. Okay, it goes through this diagram over here. There's these 4 steps here. There's 4 different programs that run, logically speaking. In reality, there could be many, many more than this behind the scenes. But at the bird's eye view, these are the logical components. The first thing that happens is your program is run through what's called a preprocessor. If I want to compile prog1.cpp, what happens is at the top of that program, if I ever say something like #include something, someone has to go out and get that file that's been included. See over here, it says #included header files. Well, that's the preprocessor. That's all that does. All it does is it takes the #include directives, and it turns out if defs and #defines, things like that. If it starts with a $, it takes care of it, in other words. Anyway, the preprocessor is what goes out and gets those pieces, all right? When that is done, it creates a temporary file. If you want to, you can just print that file on the terminal and stop the whole compilation right here. You can just run this part if you want. By default, and normally you wouldn't do that, you'd feed it through then to the actual compiler that converts the source code into, in this case, an assembly language source code file. The compiler doesn't actually output an executable program. All it does is it translates one language into another one. Okay, in this case, it's the assembly language for the platform that you want to target your software at. And that file ends with a .s by convention, okay? Once that has been created, again, you could stop the pipeline right there and take a look at that if you want to. By default, normally you wouldn't do that, all right? That then is assembled and output it into a .o file, what we call an object file, right? This is not quite executable at this point, but all the source code is gone and the instructions are in there. However, what's not in there are all the other executable instructions that might go along with all these include files over here. When you say pound include, you're literally saying, go get some other source code and copy it into my file. That's what pound include really does. It doesn't do things like load a library. No, that's not what's going on in there. All it does is copy code into your file while it's being processed here, okay? The linker can take your .o, which is by definition incomplete, because even if you pound include a bunch of data and stuff into your program, it doesn't necessarily give you all the executable stuff to go along with it, all right? So the linker says, here's your .o, which may have missing pieces, and by universally they always do. The linker goes out into your operating system and says, okay, give me all the standard parts, like, the print routines and, math libraries and whatever it is you're used to using. They are declared in a header file, okay, but they're not necessarily defined there. We'll see this in a minute. We go look at a header file, and all it really does is it says, oh, there's functions you can call, and here's their names, but the source code isn't there, okay? So it turns out there's a whole bunch of .o files and .a files on your in your system that are managed by the operating system. So it combines your code with all these other library codes, all right? And then you have one giant wad, which is your executable program that comes out this whole pipeline, all right? Now let's look and see what happens if we want to try to stop the pipeline and have a look-see at what's going on while it's going. We're going to put this big E in there. When you do that, what happens is it causes the compilation process, or the build process, I should say, to stop after the preprocessor runs and just print it out on the standard out. This is what the big E says, right? If I put a big S on there, it'll say, well, do the preprocessing and then do the language converting part of the compilation and save the prog1.s file, but stop here and leave that file sitting there so I can go look at it. And if you put a little c on there, like this, then it'll stop down here. It'll run the assembler as well, and it'll leave the .o file sitting there. Okay, so let's do a couple of these and see what happens. So the first thing we want to do is create ourselves a nice little simple program. You probably recognize how that works. Okay, let's go ahead and compile it. And what did I set in here? My wall where, and I went with C++14 for whatever reason. Not that any version of C++ couldn't compile this program. It's pretty simple and obvious. There's my source code and the -o for where to save the output. Now you can obviously, the order in which this stuff shows up in here is not super critical. So this obviously worked. Let's go ahead and run it, make sure it works. Yes, it printed out hello world, so it did what we expected it to. Okay, great. So let's say, no, I used make, which generates all these compiler lines. So if I wanted to do it by hand and I want to stop, and I could always put this in the make file if I wanted to, but I want to run it the exact same way is the point. If there's a bunch of options and arguments inside here, I need to have them in here as well. Now, these particular ones are not critical. However, if you ever see a capital D in here, that's a huge deal. The simple way to deal with this is to lose the -o prog1 and simply replace that with the big E, and no matter what else is on the line, keep it all the same, all right? Otherwise, you don't get apples and apples here, okay? So, yeah, I just flew by the screen at 1,000,000 miles an hour, so instead of doing that, I'm going to pipe it into a command called less, which allows me to go up and down and scroll through it all. So if I hit the J, it goes down. I hit the K, it goes up. I can also use the arrow keys if I want, but J and K match the Vim control character codes, right? If I hit a space, it goes down a page at a time. I hit B, it goes backwards a whole page at a time. I can hit slash and search for things in here like the word hello, because I know that this is the expanded version of my source code, that all my source code must be hiding in here somewhere, right? So I search for hello, and there it is. It's at the bottom. So down here, you can see the actual source code of my program. But what's missing was that pound include. It got replaced with this and a lot of other stuff above here. So what happens is the pound include disappears, and it's replaced with what the pound include represents. If you hit Control G in less, it tells you I'm looking at lines 28,000 through 28,451 out of a total of 28,000 lines, 451 change, right? And it also tells you how many bytes you've got in there. So my, whatever that was, 8 or 9 line program just turned into 28,000 lines of code. All right? Now, if you hit 1G in less, you go back to the top of the file. This is the line number, right? 1 is the line number, and I said G, so I says go to line 1, is what I just did there. So let's take a look and see what the compiler preprocessor gives us to work with. When it runs, it puts a little pound sign over to the left and says that signifies it's a message from the preprocessor, and pretty much what you see in here. This is a compiler boilerplate junk. Then it says pound 1, which means this is line number 1 from this file. What follows, more appropriately, is what was source code in line number 1 of prog1.cc. Okay, now that goes away and it's replaced with this. And this then says, I am line 1 from the IOStream file, which happens to come from here. Well, the include thingies all come from user include something on all Unix operating systems. They're buried in there. Not all of them, but all the system, the default ones are all under user include. So it turns out user include C++/9/ whatever, this is going to be a system dependent path of where the actual files are down below. I suspect that the 9 means I'm using like version 9 of the compiler or something like that. Anyway, the short of it is, when you say give me the IOStream include, the preprocessor goes and gets it and then recursively includes all of the sub-dependent things. So if we look at IOStream, it will internally grab onto, this config.h file. And in the config.h file, it'll define a bunch of things, right? And all these other include files will also be included. Stubs, features, long, double, cdefs, word size. And look at all this stuff in here. So I'm going to just go through at full speed. What we're looking at here, if we stop at any one place, is, a bunch of templates. C++ templates are in here. And now look at this. We're going really fast. Remember, there's 28,000 lines of stuff in here. And so far, we're looking at a lot of template things. Now, that looked like maybe it was a class. No, it's a template structure. Another one. Here's a declaration that there is a class called _defined. And there's a lot of stuff that comes in here because I said I want to be able to use IO streams. So this is, and again, remember, this is not the source code of the IOStream library. This is just the pieces that allow me to call subroutines from the library binary files, okay? So you're going to see the declarations of classes and class templates, but you won't see any real source code in here, okay? You might see some inline functions. Here's an inline function with one line of code in there that returns a value and so on. That's fine, and yeah, that'll be in the header file. But if it's actually a class that goes along with a bunch of executable code elsewhere, and I assure you a lot of this does, it will come from those .a files and other .o files that the operating system will provide, that the linker will deal with. So anyway, we could do this for an hour or hit capital G and just go back to the bottom of the file again. So anyway, this allows us to look at what shows up in here and what's actually compiled. And that's actually critical in certain circumstances when you get confused and you really don't understand why the compiler or the computer is doing something. you can do this and find out, what was actually compiled. What were all the instructions that really went into the compiler? This is one way to find that out, okay? Now, this is very rare that I use this thing. I do from time to time. It's mostly you'll do it for educational purposes more than anything else. But let's see what happens if I put a -s on there this time. Now, this won't print to standard out, as it shows inside, as it notes in here. The if you use the big E to show me expanded, the include expansions, and it'll also substitute your macros. I mentioned that earlier, all the pound defines and pound if. That's actually what I usually use this feature for, if I use it at all. I know what I'm including. I don't really need to see that usually. What you do like to look at from time to time is if you have a very complicated set of macros, you need to know that they worked correctly. That is useful to be able to see in here, and that's kind of what I use it for. Now, as this box shows, as my point is, if you say minus big E, it'll print it on standard out. If I said minus big S, it will leave a file called prog1.s. If I do minus C, as we'll see in a minute, it'll leave the prog1.0, these temporary files. There is no file when the compiler runs. In this case, it pipes it directly in. That's a subtle point. It might even be system dependent, but the bottom line is if you use big E, it'll spew on the terminal. If you use big S, it won't, and instead you will see a .s file sitting here. So my source code, which is 115 bytes in size, okay, becomes an assembly language source code file that's got over 2,000 bytes of instructions in it. So you can use less again if you want, and then you can use this to page through a file just like I did with the pipe, and you hit J and K to go up, and J goes down and K goes up. Now, I'm not a big fan of Intel x86 type instructions. I never really learned. Yes, I did, but I don't like writing in this assembly language. I find it incredibly weird. Compared to like every other CPU, I mean, dozens of processors I've programmed over the years. You come up and look at the Intel x86 family of processors, and it is just it looks like somebody that, a handyman moves in next door and puts additions on his home every 5 minutes using different architectural styles and materials that are just glued on, staple gunned, screw gunned on there. And no. I don't much care for it. It really is showing its age at this point. It was created in the 1970s and just continued to be backwards compatible forever as they, slapped a new coat of paint over the old one repeatedly to add more and more and more functionality. Anyway, the point is, I digress. That's just my opinion. Yours may differ. Anyway, you can clearly see the assembly language instruction. Move long this decimal constant into the E extended, what the heck is SI again? Segment index, whatever. You can see all the instructions and stuff in there, all right? And you got literals and labels. If you've ever taken an assembly language course, and any other language, you have this similar set of features in each one of these things, all right? So what's the point here? The point is you can see the output of the expanded includes. You can actually look at the assembly language code that the compiler outputted if you wanted to, and you can also say a -C. Now, this gets used a lot when you're dealing with a project that has more than one source file, because what it does is it leaves this prog1.0 file sitting here. All right, now I'm going to remove this assembly language file. If you ever deal with a project, I think over here we talk about that down here, multiple source files, what happens is if I want to link together multiple files that I've written, I mean, how could you do that in this pipeline? You can't. It's weird, right? Because it wants to convert prog1.cpp into its own standalone program. What if I got a prog1.cpp and like my utility functions.cpp and some other file.cpp, and I want to take all three of those, right? The way you do it is you compile with a -C, prog1.cpp, and you leave the prog1.0 sitting there, just like I did right here, okay? Then you compile your, myutils.cpp, again with the -C, and you leave that .o sitting next to it. So you end up with a whole bunch of separate .o files, all right? And that's why they call this thing the linker. It's going to link all of my .os together, in addition to other files that might come from the operating system. Then it'll combine all those together and output my one executable. So that's why you're going to see this in any project of any real consequence, right? Now, how many times you write a program with one single file? Professionally, it'll probably happen never. In reality, you have hundreds, if not thousands, of files in any real project, and header files and all sorts of stuff. Becomes a whole management project in its own right to just coordinate all those files and all the people that are involved in working on them. So you will see this a lot, okay, is my point. So that's what we really mean when we talk about the build process, or I'm building an application, right? Because you really are. You're combining multiple things together, and you're linking multiple things together down here, and you're building something out of a bunch of small pieces, right? Thanks for watching. See you next time.